Towards a large-scale federated knowledge graph, meaning negotiation in practice. The work I will talk about today was commissioned by COPE, the Publications Office of the Dutch government. Most of this work was done by a core team in which we participated, and we, that is Mark van Opijnen, advisor legal informatics, and I, Jan Voskuil, ontologist, knowledge engineer, CEO of Taxonic. We started out back in 2019, and now we are ready to combine our data with data owned by other government organizations. COPE is, among other things, responsible for the registration of Dutch government organizations. In the pertinent COPE registry, you will find all the official information about, say, a municipality. All is expressed in RDF. Cadastre owns geospatial data, and these are available in RDF and GeoSparkle. Of course, it would be nice and potentially very useful to combine these data on a map following the principles of the semantic web and FAIR data. From a technical point of view, there are no real obstacles, but getting this organized is a complex matter, which I will not talk about today. From a technical ontological point of view, to be able to usefully combine data from these two sources, we need to follow a process that essentially consists of three steps: domain analysis, conceptual clarification, and meaning negotiation. This presentation is about how we are accomplishing these tasks. On this screenshot here, you see the properties and property values of a single municipality. What is important here is that, in essence, the register of organizations has a very simple structure. For instance, there is a URI of the municipality, there is a property labeled lies in a province, and there is a value of that property, which is the URI of the pertinent province. However, the registry also registers historical information. For instance, name changes of a ministry or a merger of two municipalities. That was the topic of our presentation in 2022 in this conference. Today, I will not cover history, but keep this in the back of your head. So, we needed to enrich the COPE ontology with classes and properties that would allow one to seamlessly combine geospatial data from Cadastre with register data from COPE. The question is, how do geometries exactly relate to organizations? The process of elucidating this started with the realization that space is, ontologically, of an extensional nature. Gardens, for instance, are not. So take a triangle in a two-dimensional space, say ABC. This triangle is equal to a triangle ABD if, and only if, C equals D. Therefore, a triangle cannot be said to undergo change. In the diagram, you see two different, unrelated triangles. This is a consequence of their extensional nature. On the other hand, a garden can change through time. Here you see my fictitious garden in 2016. I bought some extra land adjacent to it, and in 2019 it was a bit bigger. It has undergone a change of state, but it is still the same identical object. It's my garden. Its identity is not extensionally determined, but intentionally, and that is an important difference. A very important standard in the intersection of the worlds of linked data and geospatial is GeoSparkle. The ontology underpinning GeoSparkle is simple and elegant. The core is the notion of feature. Features are intentional objects, like gardens. They can change through time, and they have geometries. These geometries describe space according to some descriptive system. For Dutch government organizations, NEN 3610 is a crucial piece of groundwork. It is a mandatory standard. Unfortunately, it contains a modeling error that I call the semiotic triangle transgression. It says that information objects represent objects. Geo-objects, which correspond to features in GeoSparkle, are such information objects. Therefore, according to NEN 3610, information objects can have coordinates. But that is a contradiction. If I send you an email, then it does not make sense to talk about the geospatial coordinates of the email. Physical objects have coordinates, information objects do not. Thus, the model constitutes a category mistake. It would not be fair, though, to put all of the blame for this on the authors of NEN 3610. There is an ISO standard called ISO 19101, which is considered the foundation of almost all standards in the GIS domain. The notion feature that we just saw in GeoSparkle is actually defined in terms of this ISO standard. So, let's see. The standard defines a feature as an abstraction of real-world phenomena. This is often illustrated with something like the Eiffel Tower. So the Eiffel Tower is an abstraction of real-world phenomena. Which phenomena? Right, the phenomena we refer to by using the term Eiffel Tower. But in that case, the term Eiffel Tower refers to some phenomena in the world and represents a conceptualization that in turn is an abstraction of those same phenomena. In that sense, the Eiffel Tower is not an abstraction at all, but a real-world tower with a real-world location, a volume, a year of construction, and so on. Thus, the intended definition is a feature is a real-world phenomenon. And this is exactly how the term feature is construed in actual datasets. Nobody gets confused. People fix this kind of error on the fly without even thinking about it. But in a data-centric world, where data must be fair and interpretative tasks are more and more delegated to machines, this is a real issue. I'll come back to this later on. Now let us see how we enriched the COPE ontology to deal with geometry. The green classes on the top left are a government organization and regional public body, which is a government organization that has an administrative area, which in turn is a kind of governmental area. A governmental area is a feature in the sense of GeoSparkle that is a slightly reinterpreted version of the original ISO definition. Also, governmental area is a subclass of prov entity, so that we can describe how it changed through time. As a conceptual clarification, we make explicit that a governmental area occupies a physical space, which in turn has spatial descriptions in the form of geometries. We do not see a need to directly talk about physical space, hence the dotted line. Let me illustrate this simple ontology with some instance data. Here you see how a municipality called Maastricht is said to be located inside the province of Limburg. The green circles are classes, the blue ones are individuals. Now we add the administrative areas, here called admin area A and admin area B. These are instances of administrative area, hence of governmental area, hence in terms of GeoSparkle, of feature. Finally, we add geometries to the data graph. Note that the administrative areas are so-called ontologically weak entities. One of the characteristics of these weak entities is that they are existentially dependent. If the province of Limburg would go out of existence, then so would its administrative area. There are good reasons to express administrative areas explicitly as separate entities. One of these reasons is the need to register historical change. The result is a neat separation of concerns. The graph describes the administrative relations, the topological relations, and the geometrical relations involved. Obviously, the regional public bodies are registered by COPE, and the geometries are registered by cadastre. The administrative areas could be registered by either of the two, or by both. This is still to be decided. Either way, we have a clear way forward from a semantic ontological point of view. As a side remark, let me note that the geosparkle relations here in this diagram are usually computed. The RDF relations are overloaded so that they mean slightly different things when applied to features or rather to geometries. What I have shown you is that in order to combine datasets from COPE and cadastre, we had to ascertain that the data in these datasets can be meaningfully combined. This is a process that consists of three steps: domain analysis, conceptual clarification, and meaning negotiation. Unified foundational ontology has been an indispensable methodology for this. I could not have guided these steps adequately without these tools under my belt. UFO is based on Giancarlo Guizzardi's seminal work in 2005 and has been extended and refined for almost 20 years since. It is a method designed for practical use. It is based on UML. In academia, there is a large community supporting it, and UFO is increasingly used in real-world situations. Most importantly, it helps one to create models with real-world semantics. Our brains, our neural networks, have evolved not in intergalactic space, not inside a particle accelerator, but on the savannas. Human cognition is the basis for how we understand the world. Conceptual models must take that into account. Unfortunately, however, UFO is still underused in the modeling community. And that is a problem, because today the technology is in place to let linked data do its thing. We are stuck though because of bad ontologies, like the one here, which intends to say that some customers are organizations and other customers are persons. However, it counterfactually implies that every person is, necessarily, in every possible circumstances, a customer. To be honest, before I ran into UFO some 7 years ago, I created such flawed ontologies myself. Honestly, I had no idea. Creating a solid, logically consistent ontology that is true to how the world is not something people can do without proper education. Such education is simply not widely available. Therefore, most conceptual models out there are flawed. Flawed ontologies work in applications that are custom coded around these conceptual bugs. In those cases, they are mostly harmless. In large scale knowledge graph federation, this is a serious problem. Therefore, I am convinced that we need to meet the next challenge in linked data. How do we get analysts, architects, and ontologists to use UFO? Well, what I hope may help is that we at Taxonic recently published a new one-day e-learning course in our learning environment, taxonicacademy.com. It covers large swaths of UFO groundwork and offers exercises with OntoUML. It does not presuppose any prior knowledge except some very basic knowledge of UML. So, when a student finishes this course, she can answer questions like, why is conceptual modeling important? How does UFO work? How can I apply onto UML? The target audience is everyone with an interest in modeling. It contains videos, textual sources, exercises, and more. To summarize, the process of combining datasets involves domain analysis, conceptual clarification, and meaning negotiation. Ontologies in the wild often contain hidden mistakes. Use UFO and OntoUML to guide the process. And finally, of course, register for the course.